Okay, so before we do any more examples, I want to talk about some properties that double integrals have. 6 properties in particular. In all of these all of these properties, there's kind of a counterpart in Calculus 1 or Calculus 2 for integrals. So you might see some similarities between what we talk about here and what we cover in those classes. But to begin with the first property, if you have a double integral over some region D of a sum or a difference of 2 functions, f and g, you can split that into 2 double integrals, maintaining the sum or the difference, whatever it happened to be. So this is pretty much the exact same property that you see with integrals in single variable calculus. We sometimes call that an additive property. This here, the double integral of a constant times a function, we can bring constants completely outside of the double integral, which again is just like a property that you are familiar with from Calculus 1. Some of you may have heard this before. These two properties together are called linearity. So we say that the integral operator is linear. That's not an important term for this course, but if you are taking linear algebra or are going to take linear algebra, you're going to encounter this type of property in different contexts, or these two properties in different contexts. And we refer to functions or operators that have those properties as linear. Again, not really important for us. Just wanted to make a connection if you've heard that term before. This one is probably also recognizable from Calculus 1. If f of xy is greater than or equal to g of xy for every xy within the region that we're integrating over, then the integral of the integral over d of f of x y dA is going to be greater than that same integral, but with g as the integrand. This is pretty easy to visualize if you think of f and g both as being positive functions, even though they don't have to be. If f is greater than or equal to g for all of the points on this region D, then the surface f would lie completely above g. They may intersect at certain points where the two are equal to each other, but it would be lying essentially above g. So the volume underneath this surface should be greater than the volume underneath this surface, because this one, in kind of an informal sense, has a greater overall height than this one. Again, we're not really focusing on the proof, but it's nice to have an intuitive idea as to why these are true. For number 4, if D can be represented as the union of 2 regions where the interiors of D1 and D2 don't overlap, I have a picture to show you to illustrate what this means, then the double integral over D, the entire region, can be broken up into 2 double integrals with the same integrand but different regions, those 2 pieces. So this is from your book. This is an example of what we're talking about. If we're integrating over this region here, this D, notice there's lots of different ways I could do this, but if I were to put a line right here, I've split it into 2 separate regions, which together make D, so their union is D, but they don't have overlapping interiors. So sometimes it's nice to be able to do this, to take a complicated region and break it up into easier to manage pieces and integrate each of those individually, and then just sum the results. So that's the 4th. Properties 5 and 6 are going to use this notation. When you see A of D, I'm referring to the area of the plane region D that we're integrating over. So for this, if I integrate just dA, which you notice you can think of as 1 dA, so it's like integrating the function f of xy equals 1 here, over some plane region D, then the value that we get from that double integral is equal to the area of that plane region. And I have another image from your book to help illustrate why that's the case. So let's take this as an example. D, you can see down here in the xy plane, that's the region I'm integrating over. And we know that if we're integrating the function over D, we're integrating, and our integrand just looks like dA. You can think of that as 1 dA, which means that the function that's being integrated, z equals f of xy equals 1, that's the plane z equals 1, right? So if we integrate the plane z equals 1 over that region D, you notice we have a cylinder. And the area of a cylinder is just the area, sorry, the volume of a cylinder is just the area of the base. So the volume here is the area of the base, area of D, times the height of this cylinder, which is 1. But you notice that's just A of D. It's important to note that if we were concerning ourselves with units, there would be a bit of a discrepancy here. So for example, here, because I'm talking about the double integral of a function, technically we would measure these in cubic units because this is supposed to represent a volume. Area, we would normally be measuring in square units. So the units would disagree, but that's not really the point. The point is that numerically they are the same. So this gives us a technique for finding the areas of regions, something other than a area under a curve or area between two curves, something you do in calculus too. Okay, so that's going to prove useful here and there. And finally, we have a property that does also have a counterpart. It looks a little bit different, but it's essentially the same idea in calculus 1. So this says if f of xy is bounded by these two numbers. So if f of xy is greater than or equal to little m, less than or equal to big M for all of the xy in this region D, then the integral of that function has bounds that use that m and that m, those two m's. So little m times the area of D, big M times the area of D. We can use this in cases where the integral is very, very difficult to evaluate directly, sometimes even impossible to find an antiderivative for, so we're not going to be able to integrate it directly. But the function itself may be well understood in terms of its bounds. We'll see an example probably in the next video where we deal with that. This instead of evaluating the double integral exactly, gives us sort of an approximation for what this would be equal to. Okay, so I'm going to use one of these properties in this problem up here. It says we're finding a volume of a solid enclosed by the parabolic cylinder y equals x squared and the planes z equals 3y and z equals 2y, or sorry, 2 plus y. It's very, very difficult to draw everything that I would need to draw if I was doing the full three-dimensional picture here. So I'm going to kind of do parts of the drawing and explain the parts that I'm not able to really sketch out. This problem, even though it's talking about a volume, you notice it's not just a volume under a surface. It's a volume enclosed by 3 surfaces, essentially. So we have to sort of start sketching things out and see how do we need to modify what we've done in previous examples to fit this problem. I want to start by sketching that parabolic cylinder. So this is in 3 space, like this, right? Z, X, Y. So y equals x squared. If I focus on the xy plane, that looks like a parabola in the xy plane. And it's going to continue going, of course. Because there's no z present, the z is free to vary, and so we can kind of slide that parabola up and down the z-axis to create a parabolic cylinder, which I'm never that great at drawing, but you know, it should give you a rough idea of what we're looking at. Okay, so in class you guys describe this as a taco. It's a taco. Now the planes z equals 3y and z equals 2 plus y, those are 2 planes that are kind of, from this perspective, would appear to be at a certain angle and slice this thing in different ways. When we put all of those surfaces together, they enclose a little solid that we're looking for the volume of. But notice both of these planes don't include a variable x. So kind of like in the case of the cylinder, we can think of these planes similar to how we think of a cylinder, where the x is free to vary, and it's worth looking at what the graph in the yz plane would look like. So if I go to the yz plane now, go here. Okay, so I'm going to treat that as y, this is z. Then those equations up here, y equals 3y and z equals 3y and z equals 2 plus y, those look like lines in the yz plane. So z equals 3y. I'm not going to be too nitpicky about how this looks. I'm going to say that this is the line z equals 3y, and it would actually probably look a lot steeper than that. Z equals 2 plus y. This has a y-intercept, or z-intercept of 2, a slope of 1, which is a shallower slope than the line that I drew here. So I'm going to think of this as the line z equals 2 plus y. And again, z is going to get a little confusing. Not paying too much attention to detail. The point of this is that if I were to take these two lines in the YZ plane and think of how they would turn into planes if I put everything in a 3 space. Here's the YZ plane here. Those two lines, if I were to sketch them in 3 space, can be moved parallel to the x-axis to create planes. You can imagine those planes as sort of coming straight out of the page right here. So that creates this little pocket right here. You can see this little pocket up that kind of goes up against the z-axis. That pocket is going to cut out a little chunk of this this parabolic cylinder. So that's going to indicate a couple of useful things for me. So first of all, let's see if we can determine where these two lines intersect, because that's probably going to be important. So they have a point of intersection right here. If I set the two functions equal to each other, 3y equals 2 plus y, and solve for y, I'm going to get y equals 1 in this case. So that's 1 right there. Now let's look at where y equals 1 in this graph. Y equals 1 right here. Okay, so remember that point is going to be moved along the x-axis, which we imagine coming out of the plane right here. And as it moves along the x-axis, it's going to create a line that's parallel to the x-axis. And what that actually does is it gives us a little region here in the xy plane that's going to become D. So that means I'm going to draw a third picture, this time in the xy plane. Yeah, here we go. So xy, and it's going to be that region D right there. Notice it's a parabola where the y value where I'm cutting this parabola off is at 1, which would imply that these two values here are -1 and +1. This gives me a description of the region D that I'm integrating over. So now to describe D. D is the set of all xy such that, keep bumping my stand here. The set of all xy such that, okay, so I need to decide whether I want to treat this as a type 1 or type 2. This is definitely a good type 1 region because I have an upper function and a lower function. So I'm going to say x goes from -1 to 1, and y is going to go from the lower curve, which is x squared, to the upper curve. So there's y equals x squared down there. This is y equals 1, that horizontal line. That would make that less than or equal to 1. Okay, and that's going to tell me how I want to set up my iterated integral. I'm going to finish this in the next video because I think I'm going to hit my space limit here.